I wanted also to wait to see if others could join, but Serena told me that on in the morning you were alone, also in the morning, and that's fine, no problem. So, of course, I think, just a second, I'm checking if the micro is working. It seems yes. Let me just make sure, but I think it should work, yeah. Okay, so if I will send an email to the other students, if everybody is coming from Bologna, like in the first semester, or only you are attending, or only few are attending from Bologna, if nobody from Ravenna is want to attend the lectures, we can make lectures in Bologna. It will be, yeah, it will be in Terracini, not Risorgimento, because we don't have rooms there, but anyway. We will do our best to make sure, like we wanted to do in the first semester, just to make things easier for you. And okay, so for today, we need to start. So you started already in the morning with Serena, but of course my part is separated. And my website is changed, but anyway, the content is the same. And here you find under lecture notes, the lecture notes for action on structure and infrastructures in a changing climate. And it's still to be completed. Here, for instance, I need to change because the case study is different and is not anymore the Strait of Messina Bridge. But anyway, the list of the lectures will be completed later on. So here, I just want to make an introduction to the course because it remains recorded. I basically will say things that you already know, but I want everything to be recorded. I will make it a bit quicker. And here we focus on actions. So in the first semester, we talked about modeling and we talked about adaptation and mitigation, but in terms of strategies, we didn't go into the details. The purpose of this course is to navigate the interesting topic of load estimation under changing climate. And the premise is that it's an interesting topic because there are only few guidelines at the international level on how to estimate the design loads, design project loads under a changing climate. And they are only a few, and those who are already there are still very, very qualitative, not very quantitative. The reason is that we already discussed, there is, of course, uncertainty in our knowledge of the future climate. And this uncertainty means that sometimes we know in certain locations what we think is going to change with a reasonable safety. For other variables like extreme wind, extreme rainfall, those variables that are more interesting for us, there is more relevant uncertainty. Temperature is basically something that we can predict fairly well. And for the other variables, there is a lot of spatial variability, there is a lot of additional complexity, which is related to the fact that the processes are maybe intermittent, like rainfall, maybe also wind also is intermittent, and maybe the complexity is given to more sensitivity to initial conditions, all the reasons that we already discussed in the first semester. So basically, it's not yet clear because when you want to use additional information, if the additional information is uncertain, then of course there is an increase of uncertainty. So the big question is, should we estimate the loads as we always did in the past, which means methods that are robust under the assumption of stationarity and have certain uncertainty, but maybe a lower uncertainty with respect to using the additional information that comes from our understanding of the future climate, because it may turn out that it's the uncertainty of the estimates is larger. So maybe that we can correct some bias, but the uncertainty is larger, so we are not sure whether the bias is well estimated. So if we make a correction, then there is an additional uncertainty that comes into play, which, it's a bit concerning, because already in the current situation, stationary climate, there is indeed a lot of uncertainty when we estimate loads that are related to climate. So it is an interesting topic, and therefore what we present is basically something that comes from the recent scientific findings. It's not yet included in most of the cases in any guideline and any code, with few exceptions, and therefore it is something that is to be used carefully, as we will see. And the way the course is delivered is similar to what we experienced in the first semester. So there might be some online lectures, we will see, but we are allowed to do that. We are allowed to provide the lectures in streaming and to make videos available. And then there is also the possibility to interact a little bit. We will see, so giving presentations, we will see how many students will attend, maybe also online, but let me check, nobody's here for now. Of course, at the beginning, maybe that, the students are still busy with exams, so it's this attendance today is not a good indication, but we will send anyway. And the video recordings will be made available by Serena and myself, and for myself, both on YouTube and Virtuale. These links should work. Let's see. And yeah, lecture of actions. So this is working, and Virtuale should work. Probably Panopto is not yet. Okay, yeah, it's activated because Serena already recorded his lecture, so we are perfectly fine. And then the tutorial documents are made available for myself in the usual way. And let me see if I already linked. Yeah, not yet available. This one is available. Perfect. So it's already linked. The links are still few. And because I will add the links as I move forward in Virtuale and my website here. So for now, there is a link to an introduction, which I will make today. There is a link to a case study, which is not the Strait of Messina, but it's still a case study about the coastal wind forcing. And then we will have quite a few lectures dedicated to extreme value theories, and then other lectures that will be made available later on. I anticipate that we will focus on different ways, possible solutions for estimating loads in the presence of climate change. One is extreme value theory adapted. As we will see, extreme value theory is the usual method that is applied for estimating loads related to climate, is one of the most used. But then we will also focus on simulation of future climate and therefore future forcings through stochastic processes and climate models. And then we will take an approach that is very application-based. So we will start with numbers, and therefore exercises will be included directly into the lectures. Because, extreme value theory is part of probability. Probability can be very boring if one doesn't really make several examples of applications. Probability, on the other hand, is just managing numbers. So we can also introduce the theory by referring directly to case studies. It is it is more convenient for, I think, lecturing at engineering. So the list will be completed, and then this is the calendar of the lectures. Of course, if we move to Bologna, then the location will change. And about the exam, I need to make a bit of some correction here, because the exam is organized in the same way as for the previous semester. But on the other hand, let me just correct as soon as I realize it. On the other hand, the quiz will include not only closed answer questions, but maybe also some textual question. Textual, I mean questions that may require a written answer. And let me just check. I go back now on teaching here, and I make the corrections because otherwise, okay, good. So exam, let me see, learning outcome will be assessed through online quiz, yes, plus a short oral examination. The quiz will count 30 questions with both with close answer and textual answer. Questions may include some simple computations to be completed with a pocket calculator or PC tablet. Okay. There is no penalty for answers. Yeah?
Correct.
Yeah. Let me just see. Okay, there is no penalty. No, that's fine. And with the duration of 30 minutes. Okay, good. Okay, the order will be short. It's in physical unless because the university rules motivate. And serious and issues for others. See, just 1 second. Design present because I was reminded that. Okay, good. This one. Okay. See here. Okay. Good. Good. The question related to and explain the supporting document. Yeah. And that what has been discussed in the lecture in order to assess outstanding capability to integrate the notion delivered by the teacher. Okay. Very good. Very good. So we can save this. Okay, so you already got that the exam is more or less the same situation, but there might be some very short exercises, short computations, and a duration of 30 minutes. One thing that is not written here in the exam can be taken on your PC, but you are not allowed to navigate the web. This is a news. And also you are allowed to navigate the, of course, the EOL website, but you are not allowed to navigate the web with the only exception of my website without links. So the only page that we can see over the screen is EOL or albertomontanari.it. This is the only thing that you can check. Okay. And we will, of course, remind how the exam is delivered. About the dates will be decided very soon. We cannot make any exam before the end of the lectures. So let me see, when is the end? Calendar, lectures, Unibo, 2026. I think it is June 7 or something like this. It's yeah, okay, but this is, let me see, start of 1st October, 30 September. Yeah, it's not, there is no calendar lectures. Let's see, PhD, okay, first, okay. This is, okay, you're, probably I need some time to check the page, but I think it is June. Okay. Okay. Let's see. No, this is a PDF. Okay, let's see this one. Okay, yeah, June 5. Okay, so June 5 will be probably a Friday. Let's see. I think it is like, I think it's a Friday, but anyway. Yeah, let's okay. Anyway, the week after June 5, there will be the first exam, and the number of the calls will be the same. Yeah, because they put always a Friday. So basically, starting from June 8, there might be the first exam. We will have 2 calls in June, and 1 call in July, 1 call in September, 1 call in December, and 1 call in January. So this is probably you will not need so many calls, but anyway, this is what we plan to do. And the dates will be defined, let's say, within 10 days, once that we check if we can book a room in Bologna in the lab. Because if it is in the lab, it is easier, because in the lab you are only allowed to, we can limit your navigation to specific websites. So it's more relaxing for you and for us. So basically, I think that's it. I don't think I have to say much more about the organization. You already know me, so there is no need for introducing my expertise and what I can offer to you. I think that's it. And the only recommendation is, if you see anything that is wrong here, something that you don't understand, you know how to contact me. Everything is fine. And before next week, you will receive an email asking you to confirm if you prefer to take the lectures in Bologna. And maybe that we are not in time for organizing for next week, because I prefer to wait to see if other students may join here, and then we will see. Okay, this is that's it. Do you have any question? Otherwise, we can go to the first lecture. I should have a PowerPoint here. Let me check and download the PowerPoint presentation. Let's see. Let me see. Okay, let me download. There is some Alberto Montanari. Okay, let's see. Still not there. Ah, yeah, now it is here. Okay, just 1 second. I need to make a correction, because, yeah, there is something wrong here in the link. It's better if I correct soon. Good. Let's try this. No. So let's do like this. Okay, now it works. Perfect. Okay, save.
We want to
For now, not. I think it's quite, it's not disturbing. Okay. This is to be eliminated. I forgot to do that. Okay, okay. Or let's see. Okay. And then I will make the change. Okay, so once again, we are talking about climate change. And we know that there is indeed an increasing awareness of the fact that climate change has an impact on resilience and durability of structure and infrastructure, because climate change is in a way affecting the loads over structure and infrastructures. And just let me get it here. Okay, good. And also the expected lifetime is affected. So the basic question is, how do we estimate the loads in order to take into account these changes, which depend on local condition and data availability. And I already mentioned that we cannot exclude the option that using traditional approaches is still the best solution. There is a widespread belief that indeed we need to change engineering design if we want to successfully account for climate change. Actually, this belief is still not confirmed by experience. And also, we have to take into account that in some cases, we have codes that, in a way, condition what the methods we are required to follow specific methods by codes. And therefore, before turning into innovative solutions, we have to make sure that what we do is at the same time following the codes and maybe providing additional safety, but in no way we are allowed to be less conservative with respect to what codes suggest. So basically the codes, when they are available, still suggest to follow the so-called traditional approaches. And on the other hand, we know that indeed also evidence shows that sometimes some unexpected events occur. Therefore, on the other hand, there is the requirement for updating these design solutions, these methods for estimating loads. The important thing is to keep into account that in no situation we should end up with something less conservative with respect to what the codes suggest. And therefore, I mean, when you hear about reduced reliability of current approaches in the presence of climate change, be careful, because it's not granted for sure that you end up with the more conservative solutions. And also, if the solution is too conservative, it may become not convenient. And therefore, if we end up with a design that is affected by a larger uncertainty, it may become not convenient in economic terms, to the extent that it may become not doable, not practical. And therefore, indeed, in the presence of climate change, it often happens that the solutions are so costly that they cannot be adopted. So the question is a bit tricky. We don't have to exclude the traditional approaches, but on the other hand, we have to be careful, because if there is some evidence, maybe not included into codes, but if there is an evidence, a scientific evidence that a design method needs to be updated, if we ignore this evidence, this proved evidence, and acknowledged evidence, we may be responsible in more or less the same way as if we were not strictly following the codes. So on one hand, we don't have to exclude traditional approaches. On the other hand, we have sometimes an emerging information that is not codified yet, which gives some recommendations. And but these recommendations may imply that the project becomes too costly, too demanding. So the analysis, the cost-benefit analysis, and the analysis of the practicality of the approach, the possibility to implement this design is a bit complicated and requires a careful assessment of the literature. As we already mentioned in the first semester, you have to be prepared about the literature. And I say literature, and I mean, I don't want to say any information channel, because you have to be very careful, because this is a controversial topic, and therefore you have to be very careful in taking information that is not carefully scrutinized. When I say literature, I mean the literature usually is peer-reviewed, which doesn't mean that it's correct, but on the other hand, it means that there is some check, there is some discussion, and the information that is delivered through the web or through the media is less checked. And therefore, we need to be careful, and we need to stay indeed updated. So on the technical side, what is the need? The need, the requirement, is to integrate the information that is available on climate change and related uncertainty into the estimation of actions, including, for instance, I make some examples. I will be more precise in what follows. Wind loads, wave forces, precipitation intensities, thermal loads, and multi-hazard interaction. How was this list derived? Of course, if we are concerned about climate change, we have to look at the loads that are affected by climate. So, for instance, loads due to earthquakes in the professional activity are not considered influenced by climate. In the scientific domain, there are some people that hypothesize that also the frequency of earthquakes is influenced by climate change. I think it's a very second, third order influence. We can assume from the point of view of engineering that earthquakes are not affected. Indeed, they could be affected through groundwater because and through changes of temperature, but it's the groundwater the main could be the main driver of earthquakes, because you know, if a soil is saturated by water rather than not saturated, and instead of a soil I should say the first layer of the crust, then it means that there is a different weight of this first layer, which may influence also the movement and the forcing in the deep layers, and therefore originating earthquakes. But this is considered really marginal. The typical loads that are influenced by climate are temperature, and with temperature we have also quite a good knowledge about its relationship with the concentration of CO2, because it's clear, the physics is quite clear. And therefore, I mean, temperature is anyway important for the thermal loads, like thermal expansion and etc. And therefore, it's something that is indeed relevant, also in engineering. You know that in bridge engineering, in building engineering, thermal expansion is an important load. And then there are other variables that I mentioned: wind, wave, precipitation intensity. This is much more problematic because these are variables that are more heterogeneous, both in space and time, or heterogeneous in space and rapidly changing in time. And therefore, you know, with these variables, understanding what will be the future behavior is much more complicated. So we need anyway to take into account such variability, and we are reminded that this is necessary by the occurrence of extreme events that indeed occur more and more frequently. And then the big question is, how can we do that? How we can take into account climate change? And we will consider these methods, which I already mentioned: classical extreme value theory, non-stationary extreme value theory, stochastic generation, and climate models. Look, all of these methods involve some statistics, which is, of course, unavoidable, because when we talk about climatic loads, all the approaches, even those that use deterministic model, need an estimation of uncertainty. And the uncertainty can be, of course, dealt with in several different ways, but usually some statistics is needed. What is statistics? Statistics is the science dealing with the data and data classification, data prediction, data modeling. Statistics not only includes probability. Probability is the most classical. It also may include fuzzy logic. It may include scenario analysis, because we may generate scenarios with deterministic models like we do with climate models, but then we need some statistical assessment of the output. And therefore, this scientific field, statistics, dealing with the management of data is essential. I'm making it clear because I think it is unavoidable when we talk about climate and engineering after climate change. It's unavoidable to refer to statistics, in particular probability, which is the most classical way of dealing with data. But it's not the only one, as I said, but it's the most classical. And it is the one that is most frequently invoked by codes. So the codes very often, when they suggest methods for data analysis, they suggest probability, probability distribution in particular, or probability models. Stochastic models. Stochastic is something that I will try to explain with more detail in what follows. But it is a branch of statistics, a branch of probability. And stochastic includes probability, but it's more general. And so it is necessary that we start from statistics. And it is a bit, tricky, because statistics is, on the one hand, using a lot of math, which is something that we should expect in engineering. But it makes the field a bit complicated, especially in view of the dominant way of studying at the university level today, which is not really the same thing as the past way. Today, there is the need by students to be more efficient for many reasons, and many reasons which are fully justified. And but in order to become more efficient in studying, the students tend to avoid learning by memory, which is perfectly fine, because learning by memory anyway is something that is not really long-lasting. And they tend to focus rather on a narrative approach. And this is also dominant in science. In science today, the papers that are too much technical are often not appreciated, because they require a lot of time for digesting. And in a setting, the current setting, where we are required to read a lot of papers because the scientific productivity is increased a lot and things are rapidly evolving, technical papers indeed sometimes may be not the best way to understand what's going on. With respect to, for instance, a narrative that insists on the learning of the concepts rather than the learning of the theory in its tiny details. So basically, the thesis is that if we base our learning on the narrative, we may have a better understanding of the concepts rather than focusing mainly over the math. And I give you an example. When I said statistics can be taught by starting from the theory. So the basic way is to define what is a random variable, and then to define the central limit theorem, to define, and then we focus on the applications, but at the end of the story. So basically, if we start from studying these complicated equations, we may run the risk of losing the practical utility. Instead, if we start from numbers, saying, okay, I have this series of data, I need to estimate what is the expected load during, so the expected extreme value from this process. So the time series represents a process, like I have a time series of river flow, and it represents the process of formation of the river flow. And my need is, during the lifetime of a dam, for instance, to estimate what is the max river flow that may occur with a given probability. So what is, the river flow that may occur with a chance of 10%. I say 10% because the code could suggest me to make the design based on a probability of 10%, because the codes never say the max. You have always to say, because a max doesn't exist, for instance. For river flow, the max doesn't exist. So the probability is needed to quantify what is the chance of getting this river flow. And therefore, this is what the codes do. They say, during the lifetime, you have to get the river flow for designing a dam that has a chance of 1 over 1,000, for instance, which means more or less 1,000 years return period. And therefore, we need to estimate this load. And we can start from the numbers and say, okay, I have these numbers. And then we start from the concept. The concept is I want a number that has a chance of to be exceeded during the lifetime of the dam of 1%. An alternative way is to start from the probability distribution, from the definition of probability, definition of chance, definition of what means that 10%. And then we start from the theory. And then, even without understanding the concept, we may refer to river flow or to the number of people into a room with the same thing. Without understanding the concept behind, we may derive the estimated load. So today at the university, there is the requirement of sticking more on the concept and less on the math. So it happens frequently that when I get students at the exam, they know the concept, but if they have to remember a probability distribution, an equation, they don't remember it. Or if they have to make computations, they become a bit embarrassed because they are not used to work on the practice. And therefore, nowadays, teaching statistics is a bit challenging. It's a bit challenging because I recognize that may be demanding in terms of mathematical development, but this is what we have to do. So I'm making this introduction, long introduction, to justify that we will need to refer to statistics. And I try to devise a different approach, starting from numbers. And this is what I wanted to anticipate. Extreme value theory, which is, as I said, one of the most used approach for estimating design loads in environmental engineering. I believe it's used in 99% of the consultancy activities that I have to deal with. Extreme value theory, statistics, is a classical branch of statistics. If you go to Wikipedia and look for, to Google and look for extreme value theory, you find a lot of references. And For instance, in Wikipedia, they start with an image of the Lisbon earthquake, because also they want to start from the concept, not really the math. But if you scroll down, then there is here, there are some the results like this link, the Fischer-Tippett-Gnedenko theorem, which is something that we will deal with. So this theorem is an example of the mathematical development, which is, you see, quite a bit complicated. Actually, we will deal with this theorem and we will make it very simple. But on the other hand, you recognize that indeed the concept is simple. So extreme value theory is the study of extremes in statistical distributions. And it is widely used in many disciplines such as structural engineering, finance, actuarial science, economics, earth sciences, traffic prediction, and geological engineering. So it is a very classic field. And the big question is, okay, and under climate change, so if you look at the list of links that I found under extreme value theory, you see how many links, and there is a classical book, which is, let me see if it is here. I think, no, it's not this one. Let me see. Yeah, it is this. This is a classical book on extreme value theory. It's 2006. I think it is not the first edition. It was published, I think, even earlier, and I think I have a copy of it, and I think I took it earlier, but it's not needed. So it's not needed for completing your studies, and it's not the only one. And extreme value theory dates back to, I would say, more than about 200 years ago. And extreme value theory, there is here, let me see the images. The people dealing with extreme value theory. Gamble. I think he was born in yeah, you see, about 150 years ago. And Gamble is one of the fathers, but it's not the first one. There was somebody, we will see other people that set the fundamentals of the extreme value theory. And Gamble, you remember the Gamble distribution. Okay, and presentation is here. No, okay, let's do like this. Good. Okay, so these are the methods that we will consider, and I already anticipated that we will rely on extreme value theory. And one thing I wanted to do. Here you see a lot of links under extreme value theory. But if we make extreme value theory climate change, the number of links is a bit reduced. And if you look at these links, you will find that many of them are not quantitative. So there is not a reference like you see a Wikipedia page, like in the previous example. And if you click over these links, it's not saying much. The link that I found more interesting among these, because I explored these links, because when I was preparing these lectures, which I'm still preparing, I wanted to explore these links, and I didn't find really something very helpful from the point of view of quantitative engineering. One that I found quite useful is this one, and it's a blog, basically. I found that it was quite helpful, even if it doesn't say much about how to account for climate change. But indeed, I was inspired by this website because, first of all, explains in a very practical way, but I'm not discussing it now, but it explains in a very practical way what is the meaning of extreme value theory that is focusing on the tails, because when we estimate loads, usually we have to focus on the tails. When we estimate some infrastructures, we also have to focus on the average. But the average is easier because, I mean, when you observe a process, the average is quite easy to be understood. It's the extremes that is difficult. So think of tossing a coin. If you just toss the coin and you give a 0 to the head and a 1 value to the tail, even if you toss the coin as few times as 10 times, you can easily understand that the mean is 0.5, because if you make 10 trials, you will get maybe 6 heads and 4 tails, which means that the mean is 0.4, but it's very close. But if you want to estimate what is the chance of getting 3 tails in a row, you need to toss the coin like 1,000 times in order to get a sufficient number of outcomes of 3 tails in a row. So when you want to focus on the tail of the distribution, and the tail is this one, actually, tail is also the left tail. So we should distinguish between the left tail and the right tail. Usually we focus on the right tail, but sometimes we focus also on the left. For instance, think of droughts. Droughts are looking at the low values, and drought is a risk that is as concerning as a flood. So we focus on the tails usually when we estimate loads. It can be the left tail or the right tail. And in most of the cases, it's the right tail, because in most of the cases, we are concerned by high values. But there are also a lot of cases, and drought is one meaningful example, where we focus on actually the left tail. Now, this website, as I said, I found interesting because it's very easy. And it starts from really from the concepts, you see, basic concepts. And in statistics, extreme values refer to rare events. It doesn't say refer to low probabilities. It says rare events. It's more understandable. And it describes 2 approaches. We will see them. And then it describes the distributions. And it's not very deep. And then it provides, and this was, I think it is very useful, some Python codes to make experiments. Actually, the Python code, as it is given here, it doesn't work. So I included it in my website with some modification, because probably, you know, the problem of the web is that it's rapidly evolving, and also programming languages are rapidly evolving, and therefore maybe that, you know, maybe that here, the code needed to be adjusted. Anyway, you see the moral of the story. When you look at the links of extreme value theory, or you can also look for engineering loads under climate change, and engineering loads under climate change, you find really a reduced number of information, and it is not easy, and it is not as consolidated, and this makes the subject indeed interesting. Okay, now there is also, let me see the previous one. Okay, perfect, climate models. And there are some pros and cons, which I already discussed. And the fact that there is an increased uncertainty if we want to account for climate change. This is quite obvious. If you refer to a changing situation, if you include additional information, it's quite obvious that uncertainty is increased. you know, we can explain also the larger uncertainty by saying that if we want to model a process with a non-stationary model, this means, as we will see, an increased number of parameters. For instance, think of a Gamble distribution. The Gamble distribution, in order to account for something that is changing in time, could be estimated by assuming that the parameters are changing in time, according to, for instance, a linear relationship. So we could assume, you may remember that the parameters of the Gamble distributions are two parameters, and they are estimated based on the mean and the variance of the annual maxima. So we could assume that the mean of the annual maxima is changing in time linearly. And this means that instead of having just one parameter in the Gamble distribution representing the mean and another one representing the variance, to represent the mean, I have to include a straight line equation, two parameters. There is an additional parameter. So the Gamble distribution with time-dependent mean becomes a distribution with three parameters. Three parameters means that when you estimate them, you get a larger uncertainty. And therefore, you easily understand that accounting for climate change, introducing a flexibility into a model like we did with the Gamble distribution, entails a larger uncertainty. And then the result is that you get a best estimate, which is different from the best estimate from the stationary model. It's probably larger because if we decided to use a non-stationary approach, it's because we are concerned by climate change. And therefore, if we were right in being concerned, we will get a best estimate that is larger. But if we look at the uncertainty range, it's also much larger, which means that you get in doubt because you get a larger estimate with an uncertainty range that gives to you that you have a good chance of the estimate to be even larger. And therefore you are in doubt of, okay, should I increase even more my design load with respect to the best estimate, or should I decrease it because the larger uncertainty means that it could be also lower? So basically, there is larger uncertainty, which very often puts people in confusion, and they say, okay, I don't know what to do, so basically better to do nothing because otherwise I take some very huge responsibilities. And therefore, the use of non-stationary model is a bit questioned, I mean questionable, or at least should require some careful evaluation. And then we have climate models that we can use them, but there is the question of downscaling. We already mentioned it because they work on a grid size that is usually quite large. Now, the last generation of models is producing simulation at 3 kilometers resolution, but is still something very demanding. We cannot make many simulations with such a resolution. So there is a question of reliability of these predictions. And then there is the question of the compound events, which is gaining an increasing traction because our experience suggests that when a climatic event occurs, usually it triggers a chain of hazards. A flood basically entails the risk, for instance, of infrastructure failures, so the energy failure, electricity supply failure, and we also realize that earthquakes can entail flooding because earthquakes may undermine the stabilities of river levees, and this happened during the earthquake that occurred here in 2012. Fortunately, it occurred in a season where the rivers were quite low, but otherwise, we had to rush in order to repair the levees that were damaged. and therefore there is a lot of scientific research on compound events and multi-hazard interaction, because it's extremely important to understand what could be a sequence of failures, a sequence of hazards that are occurring in a chain. Okay, so we need to change our mindset. What are the solutions? So first of all, adaptive designs. Adaptive design. What is adaptive design? Basically, it's a kind of design that allows for future modification, basing on updated climate information. And this is something that is indeed, in many cases, possible with just a little increase of the related costs. So there are solutions that can be adapted. And we have indeed to look for these solutions, because in view of uncertainty, clearly the possibility to adapt basing on the experience is a very interesting option. Here there is also some discussion about how to make this update and how to digest the amount of information that is flowing into the field. Indeed, this is an interesting question. So we are getting a lot of information about climate, mainly taken by satellites. And very often we are in the situation where we cannot really take advantage from this huge amount of information. The reason is that, understanding this data, if you try to download data, I tried today to download wave data, because I wanted to start with the case study, and if we have time today, I will introduce it. But on the other hand, if not today, next week. And I had some problems because I could find several websites offering wave data. But first, in most of the cases, the download was not possible because I got a reply like the download is too large, so sorry, you need to use a connection that is more powerful. And also, when I was successful to download them, I will show you, I found some very easy databases. Still, numbers are it's a large amount of numbers. And therefore, I mean, this is why here they mention the digital twins and machine learning and artificial intelligence is not mentioned here, but indeed this is something that we increasingly need. And then there is no regret strategies. No regret strategies, what are? It's another interesting option. The first option was adaptive design strategies. No regret means that we start with a project that no matter the future climate delivers at the current time some interesting convenience. So the project, the structure that we are designing or infrastructure is anyway giving a benefit. And this means that whatever the future climate is, people will not complain. And the resources that we put there, that is even more important, are not wasted. So it's anyway useful. So you understand that if you combine no regret strategies with an adaptive strategy, basically you start with something that in any case gives to you a benefit. And this something is not huge, because if it can be adapted, it means that you are allowed to start with a solution that is not very costly. It's not very costly, it's giving a benefit. And if in 30 years from now, the climate will evolve in a with a dramatical dynamics, you can still adapt this solution. And in the same way as for adaptive strategies, no regret strategies sometimes are very are doable. They are an interesting option, and sometimes they are not considered because you know, when you invest money, sometimes you feel like it's better to get a final solution, not a temporary solution. And this is why sometimes they are not considered. And to give you an example of an adaptive design that is very famous, I can talk about the Aswan Dam. The Aswan Dam is that we see today is the second dam. The first one was much lower in height. And the first one was built in 1901, I think, and was had a reduced height with respect to the current dam. And then I think in the 60s, after 60 years, they built another dam just a bit downstream that submerged the previous one. This is something that is turned out to be very interesting. Of course, the adaptive design, if you make total computation of what has been invested, has been more expensive with respect to building the large dam in the first instance. On the other hand, they couldn't build the large dam in the first instance because they didn't have the technology. So with the passing of time, we get more opportunities, we get more technical advancement, and above all, I'm not sure that in 1901 they had the money needed for, even if it was possible to build it, for building what is the current dam. So this way of realizing projects with subsequent advancements and no regret advancements is indeed an interesting option. And this is something that we need to consider. Okay, now key points. There is a paper that is cited on my website where I got this list of suggestions. And let's have a look. So first of all, key sustainable design principles relevant to climate change include, first of all, a particular attention to the master plan. So a particular attention to a holistic consideration. Holistic means comprehensive of what is needed for realizing the given structure, infrastructure, and what is the impact. And this is what, for instance, the recent legislation in Italy requires. The recent legislation in Italy has substituted the step of preliminary design. Preliminary design was basically a first study of the costs and solutions. And they substituted it with an evaluation of possible alternatives. And because they indeed want to get a preliminary, deeper assessment of what is the overall impact of the structure in the environment and the impact on the management, because there are management costs also related to these infrastructures, which in the past we often didn't consider. And also there is an increasing attention to the ecology and ecological services, ecologic services, which means the role of biology, of the biosphere in attenuating, mitigating the environmental impact and the management also of the structure and the infrastructure. There is an increased attention to water conservation, and minimizing wastewater production and then release, there is an increasing attention then to water conservation and to energy recovery and other natural resources. But energy is becoming something that is omnipresent, it's everywhere. For instance, now when we design water supply systems, we are also required to make a careful assessment of the opportunities for energy recovery. And also there is the need to evaluate whether the project can be realized in phases in order to basically dilute the environmental impact, dilute the use of resources, and in general, there is an increasing attention to making everything sustainable. And then, as I said, I already mentioned energy, but there is the requirement of evaluating energy savings, energy recovery with a very holistic approach, meaning that, for instance, the role of green roofs, the role of green walls, the benefits given by these solutions, and also the minimization of the CO2 emissions. This is something that is really coming into play in a very substantial manner. We need to make a careful assessment of the carbon cycle related to the construction and the management. With different indications in different countries, but it is extremely important. For instance, in Europe, there is a lot of attention on that, a lot of requirements through European deliberations, and in the United States, it was in the pre-Trump era was also strict requirement. Now is a little bit relaxed. And then, renewable energy and eco-purchasing. So basically, when you contract with the providers, there is the requirement to try to give priority to 0 kilometers products and to, in a way, avoid to overload the site with traffic, with CO2 emissions. Traffic is becoming, in recent years, really a serious problem. So there is a lot of attention of people and public administration to solutions that reduce the traffic load. And there is also the management of the construction site. A lot of attention to a management that is carbon friendly and that is minimizing waste productions and that is protecting the ecological system. And so there is a shift to the life cycle thinking. I think you got some lectures on life cycle analysis, which means that we try to optimize the cost of a structure and infrastructure and its environmental impact during the whole duration of the lifetime, instead of working on a short-term analysis. Of course, it's a complication. It's a complication, but on the other hand, we have today the means for dealing with these complications in a very efficient way. And there is an increasing amount of information about how to do that. And there is a central concept to get to target, which is what you see here, the integrated design. Basically, the concept is that we are becoming fully aware that important infrastructures require the cooperation of different disciplines. Usually, it's the cooperation between engineers, between environmental experts, between geologists. And in the past, basically, what we did was to work separately on the different conceptual part of a design project separately means that when we need a geologist, an expert in geology, then we commissioned a task to an independent expert. And then when working, for instance, over rivers, we need an expert in fisheries, in ecology, and then there was another task commissioned to another expert, expert professional. Now, we try to make an effort while preserving the value of diversity. We try to make an effort to put these persons to work together, because with their interaction and with the synergy of their skills, we can save money, save energy, and obtain at the same time better results through cross-disciplinary trade-offs and through reduction of over-design and redundancy. Because sometimes, even if you focus on different aspects, think of a very complicated infrastructure like a bridge, a huge bridge. There are several disciplines involved, and if they work separately, they cannot compensate some oversizing suggested for meeting a given requirement. They may not realize that such oversizing is already including another reason for oversizing. And also, when you plan the works, there are some different professionals that have to come into play. And if you make an overall planning of their interaction, you can maximize the efficiency. And we realize that maximizing efficiency reduces the environmental impact and the greenhouse gases emission a lot. So basically, integrated design is another change of mindset that is needed. And let me also introduce the conceptual design. So basically, the conceptual design is the first step. So we identify here, I anticipate, 3 steps in the design process. The design of the concept, the preliminary design, which is called now in Italy with another name, and I don't know how to translate it in English because it's document of doability, because it's called documento di fattibilità. It's basically an analysis that proves that a given solution is doable. And anyway, conceptual design, basically you get the overall idea of what you want to do. In the preliminary design, or documento di fattibilità, as it's called now in Italy, you get a preliminary estimation of the cost and the different alternatives. And then there is the detailed design, which is called in Italian progetto esecutivo, which is basically looking at the tiny details. And then there is the construction phase. So let's try to focus on these phases. So the conceptual design is the most critical if we think of climate change, because we need to focus on the overall concept, what I want to achieve, how to achieve it, how to build this infrastructure, how to maximize the interaction, when to build it. And so basically, this is not required by the Italian law, but it is suggested by the international literature, in which says, look, try to get a preliminary idea of all the steps that you need to make and evaluate this preliminary idea in the face of climate change, because at this stage, it's the optimal time to make to take decisions related to minimizing the climatic impact and minimizing the regret, maximizing the possibility to adapt. So think at the concept, even before thinking at the cost of a given solution, even before thinking at the solutions, try to get an overall evaluation of the target. And this is something that I can tell you in Italy is missing. In Italy, sometimes we move forward with a project because there is a demand by the population or a demand by the politics. There is maybe there has been a flood and therefore a huge flood, and therefore there is urgency in order to get a problem fixed, because people soon after a disaster, they don't think that the disaster is rare. They think that disaster may occur one day after. And therefore, sometimes the decision, the concept is elaborated in a non-rational way, in a not really logical way. And so basically, this is the right time to look at the greenhouse gases emissions, the right time to select the site layout, and to think how to minimize energy loads, to preserve the natural feature of the site and reduce land disturbance, and evaluate renewable energy options. And therefore, the idea is that of introducing an additional and preliminary evaluation of the impact of the structure and infrastructure, positive, negative impact in terms of greenhouse gases emission, environmental sustainability, and efficiency to cope with climate change, maybe in the future. And then there is the preliminary design, and the preliminary design basically requires the identification of the solutions, alternative solutions, the evaluation of their cost, and the evaluation of their environmental impact, and a verification of these solutions with respect to the concepts that I evaluated in the conceptual design. And it's indeed an essential option. What we see in Italy often is that the cost of the preliminary design is then increased about 4 times when passing to the executive design. So I often wonder why is that, because it's quite irregular. There is a rule of thumb in Italy. People say, okay, your cost of the preliminary design, I multiply by 4 and I get the actual cost. So I wonder why this is happening. I think, okay, sometimes there is inflation, and inflation now is about 10% per year. So indeed, I mean, it's reasonable that given that in Italy, keep in mind, a large infrastructure takes, there is another rule of thumb in Italy, which says if you have to build a structure or an infrastructure passing the 2 million of cost, it takes 10 years. Yeah, it takes 10 years. From the moment of the preliminary design to finishing it, it takes at least 10 years. Because you have to make public calls for commissioning the project. You cannot give a task to a professional engineer for like $500,000 of design and give it to the person that you want. You have to make a public call, public selection, and then you get an appeal to the court, and then maybe a second appeal, and therefore you have a wait. And then when we start working, typically in Italy, when you start excavating, you find some historical remains, and then you have to stop it. And then when you start, you have the protest of the environmentalists. They are very often getting to target of stopping it for a couple of years. And then you run out of money because the cost increases, and then you have to find additional money, so everything is blocked. So this is the rule of thumb, and for an intervention that passes the 100 million euros, they say 20 years. And because for dams, they say, for instance, about dam or use ports about 20 years. So basically, if you get 10% more every year, it means that, after some years, you get very easily doubled after 10 years, the cost. I think another reason for the increase of the cost is the fact that politicians, when they have to get the approval for moving forward, a good strategy is to minimize the cost, because if you start with a large cost, then you get the opposition of people, of the other political parties, and therefore very often they say, like for the Strait of Messina Bridge, they say, okay, 14 billions of euros, and actually they say that it will cost about 30, 40 billions. But it's now they even don't have the 14 billions. So if you said at this time it's about 30, of course it would never move forward. Probably it will not move forward even with this cost, but I think this is probably another reason. And then there is the reason that, sometimes when you go to the final design, indeed, you, with a more careful analysis, you evaluate that there are some criticalities, some critical condition that needs to be addressed. Anyway, the regular design should verify the sustainability, but actually it often fails in evaluating the costs. In the evaluation of the alternatives, I think that my experience, usually it works. In the evaluation of the costs, it doesn't work. The detailed design means that you have to really size everything. So the concrete, the iron in the concrete, the everything, and you have to produce everything is needed for really passing to construction. I think I am making the break here, and it is very narrative, the approach today, but I will get some more interesting information, more quantitative information very soon. Okay, let me stop the video and the mic. Okay, just 1 second. I change the password, so I solve the problem. Did you find already the logistic? Did you manage everything? Or just 1 second, I stop here. Okay. A couple of words on the construction phase and commissioning. So it's, of course, it's not environmentally neutral, and it needs to be carefully analyzed. And also commissioning is extremely important. And I'm not repeating the usual considerations, just just to remind you that also the construction phase is important in terms, and in particular, if the structure is an adaptive structure, it's extremely important that the construction is carefully planned. Okay, and so now let's look at the climate sensitive loads that we will deal with. My plan is to refer to wind velocity, waves, precipitation, and temperature. This is the plan, and then we will see. Basically, for these variables, usually we refer to the max, and to rare events, and in particular to the max. For wind velocity, usually we refer to the max. There could be also a reference to the mean when we want to estimate wind velocity for designing Aeolian power plants. But usually, actually, what we are interested in is the max wind velocity, and in particular to the gust wind velocity. Gust means the peak of the wind when there is this very reduced time window when the wind really reaches the max of the velocity. And the gust is not always taken by observations, because observations sometimes are discrete in time. And therefore, usually they refer to an average velocity. So as we will see, in some of the cases, we need to introduce a gust factor. Waves, same thing. Usually, unless we are interested in energy generation, we are usually interested in the max of wave frequency, wave heights, and also some spectral behavior. But now let's focus on these. And the precipitation, usually we are interested in duration, frequency, and intensity. And for the temperature, we are interested in both max and min, because of course they all generate loads. The good thing is that for most of these variables, the approaches are very similar. Temperature is a bit different, in particular when we talk about simulation, when we talk about estimation of loads based on stochastic or deterministic simulation. We will see why it's different. It's different because temperature is not intermittent, it's a continuous variable. Continuous means non-intermittent. And it's not really continuous in a mathematical sense, because usually we deal with observations that are not continuous in time. But we mean usually continuous to mean non-intermittent. It's better to say non-intermittent. So basically, when we measure temperature, there are no zeros, or there might be zeros for approximation, but indeed, it's not a sequence of zeros like for an intermittent process. When we talk about wind velocity, we have intermittency. For precipitation, it's a typical intermittent process. For wave frequency, also, sometimes we have what is called the calm time, the calm situation, which means no wind, no waves. Actually, when you measure waves, you measure the height of the sea level, so the measurement is never a sequence of zeros, like it may happen for wind and precipitation. But usually we also model waves with intermittent processes, with intermittent models, because intermittency is also given by a sequence that is very close to zero. It means that you may have a long time window where the variability is much lower with respect to other phases where there is a lot of variability. When you talk about temperature, usually you don't have this kind of sudden changes. You don't have flat situations that are followed by high variability. Usually it's a regular variation. But yeah, the good thing is that the methods are similar, so we can talk about extreme value theory for all of these variables. Now, if I well remember, let's discuss with the slides about what we know and what we don't know. So the effect of climate change in temperature is well known. We are in a warming period, and there is no doubt on that. It's warming, and it's not homogeneous, this warming. We talk about plus 1.45 from the pre-industrial level, but it's not the same everywhere. But it is well known. We know that, for instance, over the mountains, warming is more pronounced, and in the flat areas, for some reason, is less evident. In the southern hemisphere, is lower than in the northern hemisphere, but everything is quite well known. For wind and rainfall, the situation is not so known. We already discussed a little bit about rainfall in the previous semester. Now, let me talk about wind. climate change, it is well accepted that it should alter wind dynamics because, there is a change in temperature, which means a change in the forcing, in the generating forces of wind, because it's temperature gradient that is also generating winds. And therefore, we understand that there might be changes, but actually, it is difficult to observe this because it's so irregular, the distribution of wind, and extremes are so rare that it's really a bit tricky. We think that we observed changes in jet stream position. Jet stream is basically the jet streams are the big winds that govern the circulation in the atmosphere. And for instance, we believe that there has been a shift of perturbations, so movement of clouds, which means they are driven by wind, toward the north, and which caused an increase of precipitation in the northern hemisphere, and a decrease in the middle latitude, like over Italy. But actually, some recent observations and studies demonstrate that it's not so clear. So yes, for some years we believe we observed a shift, but in recent years it seems like there has been another shift toward the south. So it's not very clear. And why it's not clear? Because wind responds to warming in a very non-linear way. It's not a linear relationship. Linear means, for instance, direct proportion. Like the position of a jet stream is not linearly related to temperature. There are also some other disturbances and non-linear effect. And therefore, it's in particular for regional winds, the situation is really not clear. So we cannot really say for sure that for wind, there has been some kind of increase and where. For rainfall, basically, it's still poorly understood. I'm referring to the third bullet item. It's still poorly understood, but at least we understood, it seems, there is a coherence in studies across the world, a coherence saying that short-term precipitation is increased in intensity and perhaps a little bit in frequency. So it seems like while average precipitation is not significantly changed, it seems like extreme precipitation of short duration is increased in both frequency and intensity, which means that probably there are, in front of an average that remains constant, there are more intensive events, which means also more dry periods, because if the average remains constant, of course, if we have the extremes that are increased in the right tail, they are compensated in order to compensate the average by also extremes in the low tail and in the left tail. And therefore, it's not very clear. But on the other hand, there is, as I said, some coherence, like extreme precipitation, short intensity seems increased. And for waves depends on wind, and therefore still in the distribution of wave height, wave frequency, it's not very clear what is going to be the future. The waves are generated by global models, and therefore we can rely on the information by climate models, but still the situation is not very clear. But we will see in detail how we can, for each of these variables, how we can get oriented into engineering design by taking into account these uncertainties. Now, I want to close this lecture with something that is more illustrative, but with the help of figures, I think it's also more interesting. I found this report, and the European Commission developed this informal report in 2024 by deciphering the spatial distribution of global risk and the sensitivity of global risk to climate change. Look, it's not only related to environmental variables, it's risk, global risk. So what is the workflow to get to the report on the right? First of all, they start from climate and socio-economic projections. So they get hazard projections, mainly with climate models. So they generate future climate, estimate the frequency of extremes in the future climate with, of course, uncertainty, but the method is consolidated. They look for demographic projections and other socioeconomic projections, because you know that risk is related to hazard, vulnerability, and exposure. So with the demographic projection and the other socioeconomic projections, they get an estimate of exposure. Hazard is estimated with the climate models, and then vulnerability is assumed. I didn't read the report in detail, but my understanding is that vulnerability is assumed to be the same. And then they also consider the emission scenarios. And here you see two denominations, because the concentration pathways is related to emissions, and the socioeconomic pathways is related to the socioeconomic development. And basically, they both give, at the end of the story, emission scenarios, but the shared socioeconomic pathways, besides the emission scenarios, also gives additional projections of demographic and etc. And I tell you, recently, climate models, the last generation, only uses the SSPs, not the RCPs. Okay, and then they get an estimate of river flood hazards, coastal flood hazards, drought hazard, epidemics, and they in particular consider the malaria and dengue, because these are those that are more related to climate, because they are vector-borne diseases which are delivered by mosquitoes, and of course the concentration of mosquitoes depends very much on climate. If you talk about COVID, it's not very clear, the dependence on climate. And then also they evaluate the risk of conflict, the risk of tsunami, cyclones, and also earthquakes. Of course, what I expect is that the risk of earthquake is not radically changed. And then they get a series of indexes related to these risks. What is significant is to look at the change, the index that quantifies the changes in risk with respect to climate change. It is called Inform Climate Change Risk Index. And basically what you see in the map is, in color scale, the estimation of the change in risk in 2050. And here there is also an estimate of vulnerability gap, which means in the face of the increase of risk, what is the gap in vulnerability. So it highlights the countries among those that are exposed to risk that are more vulnerable in terms of, because they lack measures to decrease vulnerability. There is the reference in my website to this report, which is available for download if you are interested. And the two colors, you see the orange one and the purple one. It's the orange one is related to the most pessimistic scenario, which corresponds to RCP 8.5 and SSP 3. And the more optimistic scenario corresponds to RCP 4.5. It means a reduction of emissions. And it's also called, it corresponds to SSP 1. And you see what they envisage in terms, in these two boxes here on the bottom left. Basically, this is the map that results. Of course, you see that for the most pessimistic scenario, you have more brown colors. I don't think I have included here the legend, but basically yellow is lower, and then the orange is larger than the yellow, and the dark brown is the worst situation. And basically, they found this kind of change in risk towards 20. The color scale is here, you see here. And they found these maps of changes in risk, which is something that you may expect, because I think, for instance, the United States, it's the socio-economic projection that probably makes the country has a large risk. This is what we expect, basically, even if for India, for instance, I expected to find some more. And I didn't look in the details, at the details of the report. But I mean, this shows that the need for engineering solution is indeed very emerging. And this is the exposure to natural hazards, calculated according to the same report, and in particular the exposure to river floods. And here you can see that indeed, in the United States, it's river floods that makes a difference. Here, natural hazards, I think, I'm not sure if they include the river flood. Yes, it is included, but still it is compensated. The increase in river flood that we see here is clearly compensated by reduced values for the other risks. I mean, these maps, overall, I think the report is interesting. If you want additional information, I think this is a nice example of use of climate projections for estimating an increase, a change in any given risk. So if you are interested in river floods, then this is an interesting example that deserves to be studied, that deserves to be viewed in order to see how the climate projections were used in this case. This is not engineering. So just keep in mind that, you know, for this kind of qualitative assessments, of course, climate models are a good alternative, are a good solution. For engineering, it's less useful. Okay, and I think we can stop here, and then you will get an email from us before the next week in order to inform you on the location. My guess is that probably next week we will be again here, and then we'll check, and if there are the conditions, we can move to Bologna. Thank you very much.